So here goes to the second part of the lecture. We are going to look at the support vector machine by just drilling into the details about this optimization. And we want to show you that this optimization can be somehow modified into a form that we want. So let's start by looking at this problem. You want to solve this problem by maximizing the gamma subject to this constraint. And but solving this problem is not easy because you have all these complications that I just described. So what we can do is to follow a sequence of non-trivial tricks. The first trick is to do the rescaling of the problem. Okay, so what I'm going to do is that I want to pick a point xn that is closest to my boundary. I will just pick a point. So let's say this is my decision boundary, and I'm going to pick a point. Okay, this is xn, and then I am going to define this unsigned distance, which is the absolute value of putting this point into your discriminant function. Now you may start to wonder, if you try to pick a point according to your decision boundary when your decision boundary is still unknown, how can you pick that point? Let's just, for the moment, assume that the decision boundary is there and I can pick the point. What I'm going to show you is this. This gamma tilde, the entire thing gamma, will be gone afterwards. Okay? And so this is just an intermediate step that I need to make some assumptions. But after all these complicated tricks, the gamma will be gone. And so it doesn't really matter. Okay, so for now, let's assume that I can really pick this xn. I can define this unsigned distance of gamma tilde. Then what? Well, then since gamma tilde is defined in this way, then I can really define this gamma as this ratio of putting xn into this discriminant function divided by W2. Now, why is that? Well, it's because gamma is defined as the smallest distance from point to plane, and since xn, by definition, it is already the closest point to the plane, just put xn into it, I will be able to get gamma. Do you guys follow me? Because xn is already the closest point to the plane, and because gamma, by definition, it is the smallest distance, and therefore, gamma will equal to gamma tilde with a scaling. The scaling is the 2 norm of my W. Okay, that's a very important trick that we're taking to rescale the problem. Now, this scaling step may not be very obvious to you in the first time, but we will take this scaling, and then we are going to turn this optimization into the following. Because you have already defined that gamma equals to gamma tilde divided by the 2 norm of W, I can pretty much write this gamma in the same thing, with gamma tilde divided by W2 norm and gamma tilde divided by W2 norm. And if I write in that way, then you can see that here you have a 2 norm of W, you have 2 norm W, they can cancel. Okay? So immediately, one of the difficulties that you have an optimization variable that shows up in the denominator, that problem is solved. Okay, very simple trick, but that can help you eliminate the dependency of the variable in the denominator, and that's useful. So you remove this W2 norm. Okay, so what do we have left? Well, you have this problem. This problem says that you have this gamma tilde divided by 2 norm of W is still there. Okay, but at least it doesn't show up in the constraint anymore. Now, I can do another trick. The trick number 2 is to divide the denominator by this gamma tilde as follows. Okay, so you literally just divide the W by the tilde, and here you divide everyone by gamma tilde. I can do the scaling because I'm doing the same thing for objective function and also the constraints. Okay, this will not change the optimizer. Okay, if I'm trying to optimize over W divided by gamma tilde, it won't. The solution is still the same. Okay, so I'm just doing another scaling, and then I recognize that the problem is in this form, and then the following trick is useful. You say that I am going to look at not W divided by W gamma, okay? I'm going to look at this substitution. I will just replace all the scaled variables by the variable. Why? Well, these are just dummy variables. If I can find this W, I will be able to find W divided by gamma tilde. Okay, it's just a scalar. Okay, so I will be able to find that. So that goes to a very interesting step. If you rewrite this problem, which is a problem that involves W divided by gamma tilde, you replace all these ratios by just the W, then the problem would become this. Okay, so you can do a comparison between here, where you have 1 over this 2 norm of W divided by gamma tilde, replace it by W. Here you have W divided by gamma tilde, replace it by W. W0 divided by the gamma tilde, replace it by W0. Okay, so this is just a one-to-one correspondence. So if you can write this problem in this way, then observe what? Well, observe that the gamma is gone. Now, remember in trick number 1, I am making a very funny assumption that assume that I know the separating hyperplane, and therefore I can pick up the xn, which is the closest data point, and then I can define the gamma tilde. All these complicated definitions are gone when you go to this step. There's no gamma tilde, there's no xn, there's no gamma, nothing here. This is still the same problem as before, because what I have done so far is just rescaling and rescaling and rescaling. Okay, the optimization problem is not changed. So when you look at this problem, you realize that this is a lot nicer problem because the gammas are gone. Or the only thing that I need to deal with is just this 1 over W2. Okay, I can deal with that later. But pictorially, what it means is that originally you are trying to find a separated hyperplane with a W, okay, that will have certain magnitude. However, no matter what magnitude you have, the orientation of this separated hyperplane is not going to be changed because it's a constant scale times this entire normal vector. If you solve the original problem, you find out this W. The separated hyperplane is not changed if you solve this new problem in this space where you just scale your W by this gamma tilde. You make the magnitude of the separated hyperplane smaller. It doesn't change the orientation. Okay, what will change is that if you plug this data point into your separated hyperplane, the so-called distance will be bigger here and smaller there. But that will not affect your decision. Your decision is still +1 or -1. The magnitude of the distance doesn't matter. Is that part clear? Okay, and so if that's clear, I can just employ the last trick, which is to turn this 1 over W2 to the 2 norm of W2, 2 norm of W. Okay, so what I'm going to do is that I'm going to turn this maximum of the 2 norm of W into the minimum of the 2 norm of W. Okay, because maximizing 1 over something is the same as minimizing something. And then I can put a square because it's all positive. And then I can put a 1/2 because it doesn't change the optimizer. And so now I will end up having this problem. This problem is called the support vector machine problem that you will normally find on the internet or some textbook. Okay, it is in this form. They will call this as the support vector machine problem. This is a quadratic minimization problem because you have a quadratic objective function. You have a set of linear constraints in the inequality form. This problem is convex because the inequality defines a polyhedral, and then this objective function is convex, is quadratic, and therefore you can dump it into CVX. You will be able to get a solution, and CVX will be very happy about that because it is written in a form that it likes. Okay? This problem is called the hot support vector machine because it assumes that the data set is linearly separable. There is no soft margin, there's nothing like that. Okay? If it is, if you have data points that if you have a data set that is linearly not separable, then there will not be any solution, because you will not be able to fulfill the requirement of the constraint, because at least one of the data points will be living on the wrong side, and therefore you will have at least one constraint violated, no matter how good your separated hyperplane is. Okay, and therefore, if the data set is linearly not separable, then the CVX will tell you that there's no solution. And therefore, in the later of our lectures, we will talk about soft support vector machines that will allow you to have some kind of tolerance of misclassifications. Okay, but that will be discussed later. Yes, question.
So could you go back to that? I noticed when you have the scaling from W divided by the gamma tilde. So omega divided by that, basically the direction does not change. However, for W0, it means the position of a hyperplane in a space, right? This one's going to be shifted, right?
Yes, it will be shifting the same way.
You mean scaling or shifting?
So because because you're shifting this, okay, so because you're scaling the entire thing, you can just view it as you put the amplifying glass, okay, so the entire thing shrinks. Okay, so originally you're shifting by so many steps, but now because of the entire data set becomes smaller, think in that way, okay, and therefore the shift will also become smaller. All right, let's work on a toy example, okay. By toy example, I mean that you can really just sit down, writing out all the equations by paper and pencil, and then you can verify whether the solution is correct or wrong without going to the computer. This is an extremely simple example. You have 4 data points. They are given by these 4 vectors, okay? 0, 0, 2, 2, 2, 0, and 3, 0. 4 data points. Their true labels are -1, -1, +1, +1. Okay, so it is a data set. And then you can write down the constraints. Okay, let's say you have the vector W and W1 and W2 and also the W offset W0. And so you can write down the constraints, okay, as the following, because you can just put down the x1, 2, 3, 4 into the equation, and then you get all these numbers. Okay, so this is the set of constraints. And then, of course, you can draw out the set of constraints. That will be a very interesting exercise. But then you can also do some algebra by just combining different pairs of equations. And you can find out that the W1 has to be bigger than 1 and W2 has to be less than -1. Okay, so this 2 criteria comes from these 4 equations. And you can also try to write down the objective function. The objective function is trying to minimize this 2-norm square of the W. And you write down the 2-norm square of the W. It will be W1 square and W2 square, and you have 1/2 of that. And then you want to solve this optimization problem. And for this simple problem, you look at the constraints. W1 is bigger than 1. W2 is less than -1. And then you want to minimize this objective function. And because the problem is so simple, I can just propose a solution. Okay, I will propose that W1 star, W2 star is 1 and -1 respectively. Now, how do you check? You check whether these 2 criteria are satisfied. Yeah, of course. And then you plug this number into here. Okay, and you check whether it will reach the lower bound. And will it reach the lower bound? Well, the lower bound of this quantity, no matter what W1, W2 you give me, it will be lower bound by 1. And so if I put these 2 numbers into here, I will get the lower bound. And so that would be the minimum point. Okay? So I can solve this optimization problem without forming any Lagrangian. I can just look at the geometry, write down the solution. I propose solution, plug it in, and I get it. Okay? So I have already found the optimizer to this problem. And then furthermore, I can show you that the W0 star is -1. And therefore, this problem can be solved by using W1, W2, W0 star as this triplet of numbers. So you say that, all right, so you have solved this problem, then what? Then we can draw them on the figure. So here is a diagram showing you the 4 data points. 2 are labeled as +1, 2 are labeled as -1. And then what? Well, and then I am going to draw a line. This line is determined by the solution I just calculated, which says that W1 is 1, W2 is -1, W0 is -1. I just draw this line. Now, realize one thing, that there is a band that is not very visible on this printout. There's a band. This band comes with the separated hyperplane. And on this band, you can see that you have 2 crosses that are living exactly on this band, and 1 circle that's living on there. And that explains the name of support vector machine. Why? Well, because you're not using all the data points to construct this band. You're only using a subset of data points to construct this band. Okay? Even if you have a lot of data points, you're only going to use a few of the support vectors to define the band. Okay. Now, this notion of support vector will be made even clearer when we go to the duality. Okay. So when we talk about dual SVM, this support vector will become more apparent. Now, in this particular example, you can also calculate the distance between your data point and also your separated hyperplane, and that will define you the margin. For this example, the margin is this 0.707. Okay, so this example shows you what? Well, this example shows you that this is a quadratic optimization problem. I can sit down and write down the solution. I can draw them out on this paper, and I can calculate this margin, and I can tell you that it is indeed a legitimate solution, because this margin you can actually check is the biggest margin you can ever get. If you move this separated hyperplane around, the margin will become smaller. Okay, it doesn't require any CVX. You can just do it by paper and pencil. Okay, so now if you have this problem in general, okay, this is your support vector machine problem. You really now need to program it on computer. What are you going to do is that you are going to turn it into a standard form that the computer likes. And the standard form is called a quadratic programming problem. In this quadratic programming problem, you have a quadratic term and then you have a linear term in your objective function, and then you have a linear constraint. And so I just call this any optimization solver as QP, quadratic programming solver. All you need to dump in would be this Q, and this P, and this A, and this C matrix and vectors, and then dump it into your program, and then it should be able to solve the problem for you. For CVX, here is the example program. I wrote it a long time ago, so it was in MATLAB, but you can do a one-to-one correspondence to Python. These are just the problem set up. Okay, I'm just generating data according to certain distributions. The actual programming is how many lines? Is 1, 2, 3, 4 lines. But in fact, how many things do you need? You just need these 2 lines. Okay, what are the 2 lines? Minimize sum squared W. That's very easy. Okay, subject to y dot times this W times X W0 times all the ones minus B bigger than 0. Okay. It's literally just translating this equation to this. Okay. And then you begin CVX and CVX, click a button, wait for a couple seconds, you get a solution. Okay. Happy life. All right. Okay. That's why I really like CVX, because then you don't have to suffer in programming your stochastic gradient descent. It's a lot easier. All right. This is a comparison with the Bayesian oracle, and you see that the Bayesian oracle is actually here. It's the green line. The support vector machine decision in this example is just exactly the same. Okay, now it's not always the case, all right? And then you see that the Bayesian empirical is somewhat different. The interesting thing that you want to pay attention to is that this support vector machine regression line it actually hits the 2 data points. These are the 2 support vectors. Now, if you want to do the support vector machine in 2D, here is the program. Nothing more too complicated. It's still the same thing, okay? 2 lines. And let me show you how it will look like. This is a 2D plot of the support vector machine solution. This is the Bayesian oracle, and here is the support vector machine decision. Notice that they are different. Okay? My black line maximizes the margin. The objective function is just to maximize the margin. The green line says that I'm going to minimize the error probability. Which one is better? Well, it's hard to say because it really depends on what you want. You want robust, then black line is more black line is more robust. You want lower error, the green line is lower error. Which one is better? It's up to you. Okay, you need to tell the program what you want out of that program. Some of you asked how do I plot these curves in the past, and so I put a plotting program here. Okay, so I hope that this lecture has given you some basic ideas of what the support vector machine is, especially the first part of the lecture on how do we formulate the support vector machine problem, and then how do we convert that problem into something that you will commonly see on internet and textbook, and then give you some programming experience of how to sit down and do it on your computer. And so when we come back next lecture, we will talk about how are we going to do the dual space. That's a lot harder. And so I will encourage you to take a look at the slides first before you come to the class. And I will see you later.